I hope you see everything you need.
Yes.
Cool. So let's start. It's funny because this is the first time I'm doing this presentation. I have this like kind of weird speaking schedule that I do like 2 new presentation decks per year, and then travel with this presentation for like a year, and then I change because I get bored pretty quickly with my own presentation. So this is the first presentation. This is the first time I'm doing this presentation. So if you know me, you probably expect that a lot of slides, a lot of content. If you don't know me, you will just see what will go on. My general strategy is I want to show you as much as I can. Sometimes I will not go too deep, but we all have the same internet, so you can always find details. I focus more on showing concepts and showing my experience than going into details, because you can always find materials, and also there are slides and links in the slides to books and articles and blog posts. So yeah, wish me luck. I'm still getting nervous after 20 years of giving presentations. That's fun. So the title of the presentation is Performance Tests and Other Lies. And yeah, I will be talking, if you want to summarize this presentation in a single sentence, it's like performance tests anti-patterns. So what can go wrong when you start performance tests of your systems? And believe me, many things can go wrong. So yeah, I'm Jarek. I live in Kraków, Poland, and I think next month I will celebrate my 5th anniversary at Neo4j. So I work at Neo4j. We built a native graph database in JVM, because we use many JVM languages. It's mostly Java and Scala. And I'm staff engineer and team lead for the benchmarking team. So my last 5 years is endless fight with performance bottlenecks, benchmarking, performance tests in over different stories. I had over 20 years of experience. Most of the time I spent with JVM doing different weird things. I had short break trying to manage people, but it didn't work. And then I was an architect and I didn't like it. And 5 years ago, I came back to low-level stuff, performance, because this is what I love. Yeah, I'm speaker, coder, architect by day. So I don't know how many of our attendees work with performance tests. It will be interesting to hear if any of you have like regular performance testing, because I'm not talking about like ad hoc performance testings when things go wrong, you fix the code, you write the performance test to prove that you fixed stuff. But I'm talking rather of something called continuous performance management, when you run the performance test of as a part of your CI pipeline. So if any of you are in such projects, just share in chat. If the topic is new to you, it's okay, because I will be really trying to as I said, show you the concept, not go too much into details. In some cases, I will. So in my experience, it's like not many of us care about performance. Not many of us deal with performance tests. You usually solve the performance problems by adding more hardware, starting more instances in AWS, and it's now so easy. It's like, for me, performance testing became obsolete when cloud was invented, because people, it was so easy to scale. But now I feel like performance testing is back, because people now realize we pay a lot of money for cloud, and the performance code becomes more important also in context of the green saving the earth and climate crisis, because there are like a lot of research saying that by 2035, the majority of energy consumption will be from the data centers. So it's now not only cars causing the global warming, but also us. So that's why I talk a lot about performance, because it became, again, important. Even we have faster hardware, the thing is that we pay more for cloud, and we need efficient software. That's my thinking. So welcome to my world of performance testing. So the one and most important thing, Dr. House was not a performance engineer, but he said something that I keep repeating to my team, and it's like mantra: everybody lies. And if you become the day you become performance engineer, performance testing, performance engineer, there are like different things these people do, but it's mostly around performance. You realize after a couple of months that everybody lies, including tools you are using and techniques you are using. So this is the collection of lies I discovered. Not only I, because be reading books and doing stuff, and I will try to protect you from the lies you can see, you can stumble on doing performance testing. As what was mentioned, it's I prefer if you interrupt me, because it's quite a lot of material, and for you can forget your question, and for me it's okay and it's easier to answer directly when you see the slides or when I'm discussing the topic. So let's go into the performance test anti-patterns. The first one I call is called numbers game. So if you think about performance tests, probably your first yeah, that's a good comment. If someone tells you that they don't have performance problems on their project, they lies. There is a great quote from one of the performance engineers from Microsoft. They said, if you think you don't have performance problems, it means you haven't found them yet. So, and yeah, people think about performance tests as numbers, number of requests per second, latency, saturation of the system, utilization of the system. So if you think performance, you always think numbers. And I think this is an anti-pattern, and I will explain you why. It is anti-pattern because when you think about your performance in terms of operations per second or latency, it's really easy to be, how to say it nice, the numbers are hiding the truth. So, you see the number, but you don't see the whole behavior of the system, the characteristic of the system, scalability, configuration. You just see the raw number, and the raw number doesn't tell you a story. What was the configuration, what the system was under performance test, what was the version of operating system, what is the throughput of network, and so on and so on. You see the number, 120 operations per second. Is it fast? I don't know. Yeah, it depends. The thing is that people are so attached to numbers that they use the numbers to make decisions, and usually they use these numbers, performance numbers, to make bad decisions. What kind of bad decisions you can make? First, choose technology based on the performance numbers. So, you see one database and the other database, you compare the performance and say, if this one is faster. You don't look, and I was recently in such project helping people out, but they said, oh, this offers the performance we need, and at the same time they didn't take a look at the operational cost, setting up clusters, doing backup, restore, security, and other stuff. They made a decision based on numbers and were not looking at other capabilities of the system. the other kind of bad decisions that are driven by performance numbers is code optimization. So you make code optimizations on some performance numbers, and you say, okay, I need to optimize this code. And I saw people doing it based only on raw numbers. It looked like this, that you tweak so long your code until you get your desired number, but you don't try to understand why the system behaves the way it behaves. So this is the problem with, looking at performance only from the numbers perspective, because you don't just try to optimize this. You don't try to understand the system. You just do some kind of, monkey coding until it becomes, fast enough. What about the risk to have prod system downtime? Yes, it's exactly the same. If you, it's not only performance. It's not only about. This is a question from the chat. What about the risk to have prod system downtime? It's not about, how fast you serve your customers, but also if your customers can access the system. And there is like a third layer is like, your reputation. If your system is constantly slow or down, your reputation suffers, and people don't want to, buy your system, use your services, and then you don't get money, and then you get fired because, the business doesn't have money. So yeah, I was in a system like this when we had like every week we had a downtime for sometimes 1 hour, and it was a SaaS system, and people were constantly leaving, and when they are leaving, they were saying, okay, the product is great in terms of capabilities and business functions and features, but it's so slow and unstable that we can't work with it. So that's true. And the last thing is, based on the performance numbers, people make a decision how much capacity they need, and then they don't think about the cost of scalability and other things, and they do the capacity planning just based on raw numbers. And sometimes when you grow beyond some level of the size, the number of nodes in the cluster, the cost will skyrocket, and the complexity, the operational complexity will skyrocket, and you don't think about it when you focus just on the performance numbers. So this is the kind of, the bad decisions you can make based on the performance numbers. Probably there are many other, but this is the things I had an opportunity to work with. The thing is that, there in the complexity of current and of our systems, with the boom of microservices, when things get out of control in the complexity, especially in like this distributed system world, there are so many things that can impact performance, and so many things that can go wrong, but sometimes we are not aware of it. Or sometimes we are, but we ignore it. It's like, close our eyes and yeah, I don't want to think about it. It won't happen in production. So yeah, this is like a joke in our team. If we would be aware of all the complexity and how hard it is to model the performance, we would never become a performance engineers, but it's another lie because we like it. So the question is now, is there a value in performance testing? And is looking at this, if we make it, if it can drive bad decisions, is there a value in it? And maybe the performance tests are not only about numbers. So this is the anti-pattern if you think, in my perspective, if you think about performance tests only from the perspective of the numbers. What can happen, and this is my last few weeks' favorite topic, it's something we call in our team, and many people working in performance, something called benchmarking. And there is a really good tweet from Jeremy describing the difference between benchmarking wars and benchmarking. In benchmarking wars, what you do is you publish the benchmark. Somebody says, oh, your benchmark is wrong, and he publishes the same benchmark, I mean the same system, the same use case, but written differently, and his numbers are worse or better, then you need to respond. And this is like never-ending game, and there is no winner in this game. So this is the benchmarking wars. Benchmarking is even more interesting, and you need to be really careful with this one, because sometimes companies doing, products, software frameworks, they publish their benchmarks. What they do, they usually publish the benchmark for very specific use case, proving that their product is best in this specific use case, and they don't test everything. They just use single number, like we are super good at adding things to the database, or we are super good at doing aggregations, and they just focus on this single use case. So this is the benchmarking, but just proves that why the numbers are just a wrong thing in the performance world. Another thing that is super interesting is, I'm from Poland, and we have a saying that there is like lies, bullshit, and statistics. I believe it's in many other countries. That not many of us are trained in statistics, and it's hard to interpret the numbers in a right way. You get the number, and usually what you get is average. So you say, on average, the response time is X milliseconds. On average, you have 1,000 operations per second. What we need to understand is what average is saying is that probably the 50% of people get worse response time, and 50% of people get better response times. So average is really dangerous if you share the performance, if you look at the performance numbers. Yeah. So what you can do, what is better than looking at average, is the distribution. Because if you do a histogram and you put, the number of customers, and then you say, okay, this number of customers was served under this time, you will see how many customers are below your target. Your SLA, maybe your system has 100 millisecond response time or 50. And the average will not tell you how many customers are impacted. The histogram and percentiles are the right way to look at the numbers. I mean, the performance test, not the number, but histogram. So this is really important, is how many customers are served within the target. That's your problem. Not 100 millisecond, 10 millisecond is the rate of customers who get this expected rate of service. What is also really interesting is this is really complex topic. Is in performance, it's like you don't have the same. The question is, the percentiles for business are better than max, mean, average. Yeah, I think percentiles are much better than max, mean, and average. The problem is, that's my lesson I learned recently. It's sometimes easier to explain to business the average, max, and mean. It's really hard to talk about percentiles. Sometimes it depends, who you're talking with. The problem also is that, in performance, you don't get always the same response time for the same input. So, in a perfect world, if you send query X for customer, some specific customer, you will always get the same response. This is a perfect world, and we know perfect world doesn't exist. So in performance world, sometimes the same request will take 1 millisecond, sometimes it will take 20 milliseconds, sometimes it can run in endless loop and infinite value. For example, if you end up with some redirection loop in microservices or whatever. So this requires you to understand things like random variable, random walk, and a few things from statistics to understand why the things are they are. This is a really good article as an introduction to this problem called Performance Stats, Why Average is Wrong. So, if you Google it, it's a really good introduction if you forgot your statistic classes or never had a chance to have a statistic classes. It's a good couple of pages introduction, but helps you understand why the average is wrong. I don't think you need to be a statistician to and have PhD to do performance testing, but you need to understand things like percentiles, distribution, random walk. And this article, and there's also my favorite talk from Gil Tene from Azure Systems, How Not to Measure Latency, which touches many topics about measuring latency, but also touches the problem with the average percentile and the service level agreements. So you need to build basic knowledge and instincts, and this is the anti-pattern for me if you don't think about performance tests in the context of distribution and statistics measures. Yeah, use percentiles and use histograms. There is a really good library, and this library is for I think Java, C++, and for sure Java and C++, and I think .NET, called HDR, High Density Resolution Histograms. And it's really good. In fact, it's a standard in the performance world now. And this library is pretty good on collecting the numbers and representing them for your performance tests. Yeah. So moving to the next topic. This is the output from the tool we are using in Java world. It's called Java Microbenchmark Harness, JMH. And I think it proves my point about numbers being an anti-pattern in performance, because when you run JMH, at the end of each JMH run, it will on the console output this information. The numbers below are just data. To gain reasonable insight, you need to use profilers. You need to design experiments. You need to run baseline performance tests. And of course, you need to understand if your operating system, runtime, hardware is stable. So the number are just data. They don't give you the insights. For example, the place where it's slow, why it's slow, where you can optimize. And here we are getting to one interesting topic, because on the previous slide, we said, okay, to gain reasonable insight, you need to follow up and use profilers. And then there is an anti-patterns, and I call it profilers are lying. Basically, we could watch Nitzan Vakart. This is the JVM performance guy, and he works at Apple at the moment, I think. And he has brilliant presentation about profilers. I highly recommend it. It's profilers are lying hobbyist. So basically, on one side, numbers don't tell you the whole truth. On the other side, profilers are constantly lying. This is, the Nitzan presentation is hour long. I will just give you 2-3 slides of explanation. So if you think about profilers, you have two choices when you build profiler. You can either decide to use the sampling profiler. So, every 30 milliseconds, you take the snapshot of your state of your system, your thread stacks, your counters, performance counters, and so on. And, the problem with this approach is if your method is faster than the sampling rate, you sample with, 50 milliseconds and your method has 1 millisecond execution. You will not see it. So with sampling profilers, you don't see the whole picture of the system. So people are saying, okay, let's go and use instrumenting profilers. So the instrumenting profilers are modifying your code, adding, injecting little pieces of assembly or bytecode and collecting every information. The problem is they are really precise. That's true, because, this is no sampling. Every invocation is cached and recorded. The problem is that you are running different code, because this is instrumented code. And instrumented code will have, for example, in JVM, it will be optimized differently. That's the way JVM works. You will have different memory usage because the instrumentation needs to store counters, thread stacks, and all the sampling information somewhere. So with sampling, with instrumenting profilers, you get better insights, but on the other side, you are benchmarking the different system than running the one that will be running in production. This is not fun. So, choose your pill. Do you want to be light, or do you want to run the different system, performance tests on the different system? And it's even worse with managed runtimes. Java, C#, Python, JavaScript, Ruby, all the languages which are not compiled to native code will suffer from even more problems when profiling, like, garbage collection pauses, safe pointing, code optimizations, JIT in Java, when you can have different versions of the same method because it was optimized by speculating compiler. So you will be watching different versions of the same method during the performance run. So don't trust profilers. As you can see, you have to be critical looking at the profilers numbers. You need to, before you run profiler, you need to, in your head, build a model what you would expect to see. Okay, what you are looking for. Maybe not expect to see, what you are looking for. Try different profilers. Yeah, use 2 or 3. We usually have in our work 3 profilers we are comparing. And recently, I was a part of big experiment in our company when we are comparing Intel versus ARM, and we were running like 2 or 3 profilers at the same time, comparing them, and we found the problem in one profiler that was not visible in the other one. What are the most biggest reasons to use profiling tools? I think the question is, what are the most biggest reasons? I think to understand what your system is doing and where is the bottleneck. Because the numbers will tell you we are slow. We will not tell you where we are slow. We need profiling. I would say 100% of time you need profiling. So if I can share some insight from our work, what we do when we run performance tests, and it's like, it's another secret, many people do it. We run our performance test twice. We run our performance test without profilers because, the profilers have overhead that can change behavior of the system. So we run, like we call it measurement run. So we run the performance test just to get the numbers, latency, throughput, and we use these numbers to do regression analysis and regression hunting. And then on the same configuration, exactly same amount of data, exactly same environment, we repeat the experiment with profilers. So when we have regression, when we see like numbers are going down, okay, why? So then we can open the profiling recording from the run that we saw caused the problem, and we can say, okay, it's slower because this is happening in the code. You can open, the fast profiling recording and slow path profiler recording, compare, and it helps you to, with solving the regression, performance regression problems. And it also helps you optimize the code. Yeah. So, like the reasons you need profiling, one is to fix the regression, and the other one is to optimize your code. Because sometimes you want to make things faster. They are fast, but you want to make things faster. But these are different cases. We are talking really now about, generally profilers. My talk is not like I'm JVM guy, but I'm not connected. My talk is like technology agnostic. So we are talking about, in general, using profilers when doing the performance runs. Another solution is to look at performance counters. So profilers will tell you, which method was called from which place of the code, how much time it took, and so on and so on. And then we have metrics and counters which tell you, okay, there was so many garbage collection, and the garbage collection took so many milliseconds. We had so many thread pools and so many connections to the database. So what helps you is to look at the profiler and the performance counters at the same time. Because if, for example, you see something in the code and you don't see it reflected in the value of the metrics, probably somebody is lying. The one that's lying, it's probably profiler. Not always, probably. Okay. So the solution: design factorial experiments, perform baseline tests, make sure that you use the stable environment. Don't allow like auto upgrades. Make sure that this is always the same operating system, the same hardware, and so on. Ask for reviews of your code performance test. The more people look at it, the better. And don't assume the numbers will tell you what you want them to tell you. It's like we recently had a case with Intel and ARM when we said it has to be faster on ARM because people are talking about ARM is generally faster for the types of workloads we have. And when we ran and we found that in our case, ARM is slower only for writes, it was like, oh, something is wrong. It's like we haven't thought that basically maybe our system is slower under ARM. Our thinking was, okay, everybody is talking that ARM is faster, so we assume it has to be faster. It wasn't in our case. But really be careful to not be fooled by numbers. So yeah. That's the question. Have I skipped the slide? No. If the number is an answer, what is the question? And I think this is a misconception quite often, that, performance tests don't answer the same question. Different performance tests answer different questions. You need to think what kind of question you're asking to the performance test. And I will explain it in a minute what I mean. So basically, there are layers of performance tests, different types of performance tests, but you need to design them in a different way because they answer the different question. You have the latency test. So what is my end-to-end transaction response time? You have throughput tests. So how many transactions you can run on the system? You have 4 machines, you run load generator, and you want to see what is the number of requests per second. Then you have the load test when you say, okay, is our system capable of handling 20,000 transactions per second? So you are not looking at the capacity of the system, but the maximum capacity of the system. You need to design the experiments for the kind of answer you want to. Then you have stress tests. So when you want to, my favorite test, what you want to do is basically bring your system down on his knees. It's like kill the system, run as distributed DDoS, and see at what point the system breaks. Okay. What is interesting is observing when the system breaks, do you lose for example, consistency in your system? That's interesting. Like, what is the side effect of system breaking? Then you have endurance test. So then usually you run tests for like 1 hour, 2 hours, but some anomalies, and they are like the worst one and trickiest one, is they show up after 48 hours. So then you have endurance test when you run the performance test for longer periods of time to be able to be able to see if we have some small memory leak, or the transactions, the connections are not returned to the pool, something that will take time to our system to break. Then, of course, you have a capacity planning test. So basically you run, with 4 machines, 8, 16, 32, you add more hardware and you see how your system scales when you add more hardware. And degradation, no, it's not. It's like regression. Yeah, the question from Sava is degradation similar to regression? Regression is, you run tests, you have 100 milliseparation per millisecond, then you run, you have new commit, new version, the system is slower. This is regression. Degradation is you run the system and you fail one of its components. Like it's interesting in microservice, it's super interesting in microservice world. You can think about it like some kind of chaos testing. So you have a microservice architecture, you kill one of the microservices, and then you run performance test. Because in the microservices world, you have this concept of retries, circuit breaker, and other things that protect you, supposed to protect you from the problems in a distributed world. But if they are implemented in the wrong way, the values of retries and values of circuit breaker, it can slow your system down, because in distributed systems it's like dominoes. The performance of degradation of performance of one component can destroy the whole system. So degradation is more about testing the performance when the system is not fully operational. So when you design, if somebody comes to you and say, okay, write me performance tests, your first question should be, which one? Are you interested in latency? Do you want to do some capacity planning? Do you want to understand if you have like memory leaks? Or do you want to understand what happens when the system is partially broken? Some parts of the system don't work. So this is the second question you need to answer before somebody asks you to do the performance tests. There is one last layer of performance tests. It's called microbenchmarks. Microbenchmarks are, it's the hardest, I think, the most interesting, but you need to think of microbenchmarks as a unit test of performance world. So in the performance test, you set up the whole system, databases, microservices, integrations, you run. Microbenchmark is you take specific part of the code and you benchmark this specific part of the code, because this is the hotspot. This is the hot path in your application. It's easier to understand things in microbenchmarks than to understand things in the whole system. So sometimes, usually, our path is we write the large performance test, we set up the whole system. Once we find the bottleneck, we write micro benchmark just for this bottleneck. So it's easier to work with because you have faster turnaround with micro benchmarks. So it's like unit test. You can think about it. I think about it. Oh my God, 15 minutes. We'll do it because I still have a lot of material and I hope I didn't bore you. So the thing that is quite often a case is people think latency is throughput or throughput is latency. People think that you can give somebody latency number and he will calculate the throughput, or you can give somebody a throughput and he will calculate latency. It's not like this, okay? Because like latency is a function of the system utilization. So the more system is pushed and the more transactions you have, the bigger number of requests per second, the latency will grow. Now there's like nice formula to calculate it. So basically, throughput is not latency. The latency is a function of throughput. It depends, the value of latency depends on the throughput of your system. So the question you need to ask to escape this anti-pattern is, what is your system latency for this number of transactions per second? This is the valid question. saying what is the latency of the system, your response should be, okay, for what kind of queries per second? What is your queries per second? And then I will tell you what is the latency, okay? So you cannot calculate things. This is hard. And I was thinking that this deserves like another presentation, because when you build the performance test, one of important, like for me, it's foundation, is the workload. So you basically, the data set, your databases, the queries you are going to send to the databases, and parameters for these queries. And if you get it wrong, everything will collapse. Okay, we have a question from Sava. How microbenchmarking looks at practice? Is it like to create performance units? Yes, exactly. So you test single function. If you find using the higher order tests, like the large scale system performance test, you found a slower code and you want to optimize it, then you write the micro benchmark that just calls this function. Why it's good? Because then you have faster turnaround. You just run it on your machine or like dedicated environment, and you don't have to restart the whole system because you did that small tiny change. So with micro benchmarking, you have better response time, and it's easier to work. And for example, in Java micro benchmark harness, it looks like JUnit tests. You have a method with annotation benchmark, and almost all it is. So modeling can hurt your brain. I will save you from this discussion. Maybe next year I will do the presentation about modeling. But what can go wrong? When you build the database for your performance test, you need to understand what kind of actors you have in the system. Do you have customers? Do you have HR reporting? Do you have maintenance people? What kind of people you have in the system? Because different people will ask different questions to your database or to your services. So you need to identify what kind of actors you have. Maybe you have people buying a lot of small things, and then you have people that buy things that have 100 things in the basket, in the shopping cart if you're in the e-commerce. So you need to find the actors in the system. Then you need to construct the data set. So how large the database is. Is it like 1 terabyte or it's like 200 gigs is enough? Then you need to understand traffic shaping. Do you have a flat traffic to your system, or you have ups and downs? You have seasonal maybe traffic to your system, or it's nice in the morning and you get the majority of the traffic in the evening. Then you need to understand what kind of operations you can do on your system. So removing, adding the product to the cart, updating the number of my previous job was e-commerce site, so I will use this thing. Adding stock to things. So you need to think about the operations, and the next step you need to think about the dependency. So when if somebody is adding something to the cart, it's probably that the next thing he will do, he will buy stuff from this cart. So you need to design your performance test that like mimics the behavior of your people, your customers. Then you need to think about the interleaving. So some queries log the database or log records. So you want to test these examples when you have access to the same, document in the database, or you have access to the same row in a relational database, or the same node in the graph database. So you need to make sure that you will test, the contention. Then there is the time and data retency, because people are leaving your system. So, people are removing the accounts, people are removing products from your store. So you need to model this as well. So as you can see, I just name a couple of things. When you design the data set and your workload and your scenarios, you need to think about all of these things. And it's super hard. That's why sometimes for some cases where like you can use existing workloads and you can use existing scenarios. It not always works. It depends on your domain. And there is one more problem with datasets, and this is something I learned, working for 5 years as a performance test engineer. It's all about cardinality indexes and data lifeset. So cardinality of your data, how many products is in the bucket, in the basket, how many employees in the department. So, if you have one-to-one relation, like one employee in one department, and this is your performance environment, and then you go to production and you have 2,000 people in the department, it can, bring your system down to your knees. Understand indexes and understand lifeset. What is lifeset? This is the amount of data that needs to be in memory. So the active subset, actively used subset of your data. Because I think, 20 years in business, at the end, it's always a database problem. So majority, I would not say all, but like 80%, of cases, the problem is the database. It's not the database per se, but the schema of the database, the queries we designed, but we end up solving the database problems. So that's why the data set, you feed your data before running performance tests is so important. So when you design your queries and your data, make sure that you always have like similar cardinality, because the problem is if you sometimes return one customer and sometimes 200, like you have HR system and you have departments, and departments have people, and your data set has sometimes 1, sometimes 200, what will happen, you will get unstable results and you will see a lot of noise, and you don't want it during the performance bottlenecks. I mean, performance tests. You want to see stable system, like because you want to find the performance bottleneck, not the edge cases. Okay, so you need to say, okay, by design, most of our customers will have 200 people in the department, and this is how you design your database. Otherwise, the results will be jumpy. Sometimes 100 milliseconds, sometimes 10 milliseconds, depending on which part of the database you're fetching. And you need to be really, like look at the variance. If you have a performance test and sometimes it's 100, sometimes it's 10, it's a bad performance test. Because based on such tests and results, you won't be able to make a decision if this is regression or not. You will say, oh, it's within the 110 millisecond range, that's fine. No, it's not. The problem is the test is broken, and it's mostly broken because the cardinality is distributed. So what we do sometimes in our system is when we run performance tests, we measure how many records and rows we returned to make sure that we have stable distribution. So the size of the request and responses are, similar. They don't have to be the same, but within some, range. So this is the example from one of our systems where we say, okay, in this second, we returned, result with this number of rows. So this is the seconds on x-axis, and y-axis is the number of rows. So, this is like example of a really bad test, because you have sometimes you return like 10, sometimes you return 1,040,000 records. It's unstable performance test. What we do to track it against statistics, we use something called coefficient of variation. And this is like statistical measure, which shows you how stable are your measurements. Okay, and if the coefficient of variation is large, you need to do something to make sure that you have like repeatable response times during the performance tests. The other thing that can hurt your brain, and people ignore it, is the test environment. So, you don't run your test performance. I know this meme, I don't always write performance tests, but when I do it on production. So some people will have a test environment for performance tests. And then it's like another collection of problems you need to think. Instance sizing. You cannot afford to have a mirror copy of production unless your production is a single server. If you have microservices or big data systems or streaming, you will not create exact one-to-one copy. So you need to decide what kind of, is it a half or 1/4 of the of your system. You need to make sure that your test environment has a good network isolation and infrastructure isolation. What I mean by infrastructure isolation, I mean you have separate database for production and separate database, like an example, and for performance tests. Okay, you don't run it on the same machine. Configuration, it will be different, yeah, because you will have different instance sizes, you will have a different number of components, you will have different networks, so you will need to change the configuration as well. Some components will need to have the same configuration, some you will need to adjust to your sizing. And last thing, if you, on your performance test path, do integration with third party, like payment gateways and so on, mock it. I know people don't like mocking, but you are not here to find the performance problem of PayPal or any other payment gateway. You are here to find the performance problem in your system. You have SLAs with your vendors and third-party integrations, and this is your protection. So you rather create mocks that return responses in the same time. It's always 20 milliseconds, whatever you choose, but you don't rely the numbers on performance tests on some hiccups in third-party integrations. We are getting close to the end. And you need to remember that it will always get worse in production. So if you have good numbers on 10 milliseconds in performance environment, you cannot compare it with production. So we do it only to catch regressions. Okay, so we run on test performance environment just to catch regressions, not to compare with production, because you cannot compare these two systems. And last thing is load generators are lying. So the tools you are using, like JMeter, they are okay. Basically, it's better. It used to be really bad because most of the things suffered from something called coordinated omission. So this is this problem when your system under test becomes slower, you are also slower at sending requests to the system. So when the system under test becomes slower, you also are sending less requests, which is not true, because in real world scenarios, what you will do is, the customers won't stop. They will just, even send more requests, like clicking Control R and refreshing the page. So once your system becomes slower, your customers will still be active and sending requests. And this is coordinated omission. Really good blog post from guys from ScyllaDB about coordinated omission, and highly recommend to read it. Fortunately, we are slowly running out of time. How you can deal with it, with the coordinated omission. So basically, in performance world, you have two type of systems. You have open model systems and closed model systems. The open model system is the request arrive independent of how quickly the system process requests. So this is the real world. You don't care, customers are just sending requests. In a closed model, you execute query, you run, you wait for response, and then you execute the next query. Okay, so the triggering of the next request depends on the response from the previous. This is unrealistic. So what we want to do is to build open system models, because this is the real life. Okay, just to compare it. With closed system, you make a request, you wait, and then you make the next request. With open, it looks like every request is executed on a separate thread or pool of threads and so on. So yeah, okay. So how you deal with this problem that, you know, the system is getting slower, your system under test, and you still want to, you know, send 10,000 transactions per second. So what you do is usually what you do, you create a thread pool that executes the connection. And then you have two solutions. It's like static schedule and dynamic schedule. The static schedule is you try to always execute at the same time. So if you said, I will send query every 10 seconds, you will always try to send it 10 seconds. It means that if the previous query took 9 seconds, you will not wait 10 seconds to execute the next one, you will wait 1 second. So you just adjust to the system being slower by, you know, sending things faster. So this is the static schedule, and the dynamic schedule, you basically wait minimum delay between requests, okay? And you just try to pray that everything will be fine. So this is the queuing approach, and static scheduling is the solution to the coordinated omission problem. Oh man, this deserves separate presentation. How you do it? It's basically what you do is, okay, you calculate now, say, okay, this is the time now. Now I said, okay, I supposed to run this request at this time, but, you know, system was slower, but, you know, intended time, you know, by schedule, I should run it at X. Now it's X plus 1. So I take into account the fact that I was running, I had to wait. My system was busy, okay? And then you like use this calculation to calculate the latency correction. I'm speeding up things. Guys, sorry. I know which slides I will need to remove with my future version of the presentation. Oh, last thing, sorry. This was not the time. The problem is that measuring time is not something we can trust. Because first, it takes time to measure time. That's the one thing. The other thing is you don't always have 1 nanosecond, 1 millisecond granularity, okay? Most of the system have, you know, 30, 50 nanosecond granularity. So if something is faster, you will not notice it, okay? And then you have the scalability problem is, you know, when you try to access the clock from multiple threads, then you welcome contention and things can go really slow. This is example, great article from Alexei Shipilev, nano trusting the nano time, and according to his measurement, you have usually 30 nanoseconds granularity, and to take current time, it takes 50 nanoseconds. And it depends on your CPU, operating system, and so on and so on. So it's not that easy. Whew, we reached the final boss. So I'm closing the presentation. I'm open for questions, of course, but I need to present you, the final boss. And for me, the final performance anti-pattern is not having performance test. Surprise, surprise. I think it will matter more and more in coming years. And there is even, if you look for Google, like initiatives called green coding, where people are, taking special care about the programs running faster and be less and more energy efficient and, less polluting the planet. So yeah, I hope we will see more focus on performance in coming years, but yeah, we'll see. Thank you. You are my guinea pigs for this presentation. So any feedback is welcomed. I already knew where I spent too much time, and I should spend more time explaining coordinated omission because it's more complicated. Yeah, ChatGPT can do performance testing. I hope not. I hope not. And we had recently discussion in my team, like, will we lose our job because of ChatGPT? And my team was like, nah, because somebody will have to performance test with code and then improve it. So we are trying to be optimistic. Okay.
Okay, guys. So if you have, I see that we still have a question in the chat, but I just want to remind everyone, if you would be so kind, please choose in right option to everyone. So your question will see not just Jarosław and me, but everyone participants in the chat. And if you don't want to type a question, just push raise hand button below and I'll unmute you.
Yeah, we have a question. Oh, I lost the question. Okay, it disappeared.
There was a question and somehow it disappeared.
1 sec. Okay, waiting for some. That's okay. I know it was a lot of information. Why the volume? Oh, okay, we have a question. Why the volume testing is missing the list between stress and capacity? Oh, okay. Question is, what do you mean by volume testing? Because if I think right, it's called load testing in the taxonomy I showed. You know, this is one of many ways to like define the layers of performance tests. So some books will have different ways of describing the layers of performance testing. So I chose it from the Java Performance Companion book because I mostly do JVM, and in Java Performance they use the load testing. We're not talking about volume testing, but yeah, it's sometimes you have the same name, a different name for the same stuff. I hope I answered the question. Okay. So I think we have now free tools. Yeah, so we have free tools in our performance testing. It's Gatling, it's JMeter, and it's K6S. Yeah, I think it's from the guys from Grafana. I was not using it. So I have mixed feelings about JMeter. The problem with JMeter is that this is like drag and drop tool. Yeah. So and you have UI interface, you can drag and drop and design your scenarios. But the thing is, it's really hard to work in a team with JMeter. So usually if you have one engineer, JMeter is fine. If you have a team of engineers working on JMeter saves things in XML. It's hard to merge it. It's impossible to work in using GitHub and the regular workflow. So there are some DSL wrappers around JMeter, so you can use Groovy or Java and design your performance tests in Java or in Groovy using JMeter as an engine. There are a couple of wrappers. You need to be careful. Some of them are not maintained anymore. JMeter has, I think, wider adoption in industry because it's older, and there are like cloud solutions which support like Blaze Matter which allows you to run distributed load tests. So this is like JMeter. Gatling on the other side, it's newer. It's easier to work because you have, it was originally designed in Scala, and now you have a Java DSL. So it makes work in a team with performance tests much better. So I would say, if I would choose today, I would say Gatling. If you do this kind of ad hoc performance testing, so you don't run it on CI and so on, but you need to just run it from time to time, JMeter is fine, and it's sometimes easier for people to explain what we are actually testing, because you have nice tree of components and steps. So I would vote for something that codes in real language. K6 is okay, but I haven't used it. And I think it's mostly targeted to HTTP systems. With Gatling and JMeter, you can test, Kafka, you can test databases, you can test HTTP. So I would choose one with like slight bend towards Gatling. I hope it answered Lukasz's question. Okay. So yeah, I think we're good for today. Thank you for listening. I also send slides, and yeah, if you, oh, coming back to benchmarking, we have, okay. Coming back to benchmarking, what could be the best tool for it? Must be the most lightweight console tools or code? So it depends on your platform. So if you are in the JVM world, I would say JMH, and just don't waste your time looking for anything else. It's de facto standard. Like, parts of the JDK code is tested by JMH, and they have benchmarks written in JMH, and everywhere you see like comparison of performance of some parts of Java, you will always see a JMH benchmark. So I cannot speak for other platforms, but for JVM, it's JMH. It's really lightweight. It's easy to run. You just focus on the code. The whole infrastructure of running profilers is built in JMH. So yeah, I would say for now, it's the only answer in Java world. I cannot speak for everything else.